Hi, everybody. So this week we are going to look at material from sections 1.3 and B.4. We'll go ahead and start 1.3 lines. So the idea with a line, above all else, is that you need 2 points to describe a line. You just have 1 point, you could draw a whole bunch of lines through that. For example, just have this 1 point, I could have all kinds of lines going through there. But if I have 2 points, there's only 1 line that you can draw through those. So we need those 2 points in order to describe a line. Now, once you get those 2 points and put the line in play, one of the things that comes in, and the big concept, or one of the big concepts, I should say, with lines, is that you want to start looking at the slope. You're describing a line to somebody else in mathematical terms. Slope is going to be one of the first things that you're going to use to describe it. So in general, with slope, you can think of this as the rise over the run, which is really equal to the change in the y values divided by the change in the x values. So if we take a look at a slightly different example here that's not so cluttered, and give myself some tick marks here. You see that if we put in a little point here and put this other point here, go ahead and connect those with straight lines I can draw at this point. And what I'm going to do to make this idea of the rise over the run stand out is those little dotted lines there. And the idea here that I want to really point out with this change in y values is that from one point to the next, you can see that there is a change in the y. I started down on the left and I ended up over here, up a little higher on the right. So we would call that the rise. And in this case, we do have what they would call a positive rise, or you can think of it as a positive rise. Our y values are getting bigger as I'm moving from left to right. And then down below, well, how far did I have to go before I saw that amount of rise? And that's going to be the run. And that's going to be between the 2 x values of our 2 points that we're given. So the change in the y values gives us the rise, the change in the x values gives us the run. Now, mathematically speaking, if we wanted to figure this out, if we were just given 2 points, we would use this formula and this notation for slope, the letter M. And letter M is used instead of letter S, which makes a lot more sense to me and pretty much everybody else. We use that letter M because, from my understanding anyway, it comes from a French word for mountain, pain, I think is how they say it. So that's why we use the letter M for slope instead of letter S. And it is very consistent. Any other math class that you would go into where they talk about slopes of lines, you're going to see the letter M popping up. Now, what about these subscripts? I see a little y sub 2, y sub 1, x sub 2, x sub 1. Well, the subscripts, it's just a way for us to write the letter y twice, but keep track of a difference from one point to the other. And the subscript, let's say subscript 1, is referring to the first point that you identify. Subscript 2 would be the second point that you identify. So, for example, I wanted to figure out the slope of these 2 points. And let's go ahead and get 5, 2, and 2 comma negative 6, one of these points would have the subscript 1 attached to them, and the other point would have the subscript 2. In practice, it does not matter. And I encourage you to try this yourself after you've watched through this video and see that you will get the same answer. You know, no matter how you switch the subscripts around, as long as you are consistent from point to point. What I mean by that is, if you're going to call this x2, well, the y value in that ordered pair, it better be y2. And you don't want to have x1 and y2 mixed together, or x2 and y1 in the same point. Use the same subscript within the same point. So over here, following that, I'm going to call this x1 and this y1. So if you're finding that you're getting the wrong answers on these, my number one recommendation is to go ahead and quickly label the point first, as I've done here. And that's going to save you a whole lot of hassle and headache. And once you have that in, we can go ahead and say, okay, well, m is equal to this y2, which is 2, minus the y1, and then over the x2, which was negative 5, minus the x1. And when you work that out, the numerator, you're going to get a positive 8. So remember, a subtraction of a negative will make that a positive, so 2 plus 6 will give us 8. And then in the denominator, we're going to have negative 5, take away 2 more, and we'll get negative 7. So I would say here that this slope is negative 8/7, or negative 8/7, or negative out front 8/7. One thing I want you to be aware of in math in general, if you're writing a fraction that happens to be negative, you can attach that negative to the denominator, the numerator, or put it out in front in the middle, and they all mean the same thing. Just keep that in mind. I don't have a preference for how you write it, just know that they're all the same. So again, with this, just to reiterate, I could have labeled these points differently. I could have called this x1 and y1. I could have called this x2 and y2. And I would have gotten the same answer plugging those in to the m formula. I highly encourage you to try that and verify that result. So get that out of there for right now, just so that it doesn't confuse the issue. But that is how we get our slope. And what this tells me, this negative 8/7, is that I should be seeing, as I move from left to right in my coordinate system, a line that has y values that get smaller as I move in that direction. So let's go ahead and plot these points. Negative 5, we'll go ahead and put that back here, and 2, I'll put this right there for the sake of somewhere. Stop there. And the second point, we are at 2 and negative 6. So we'll put that here. And when I connect those 2 points, we do see, yes, indeed, as I move from left to right, my y values are getting smaller. Started at 2, ended up down at negative 6 for this example. Okay, so we do need 2 points to get the slope. Sometimes they might give you the slope. You don't know what 2 points were given originally to end up with that slope. Because in fact, any 2 points I pick off of any line, they're always going to have the same slope when you work out the math there. I mean, the slope of a line does not change. So I can pick a point here, pick another point here, and when I do the math, y2 minus y1 over the x2 minus x1, I better, as long as we don't do a mathematical error, get the same negative 8/7 result off of that line. So sometimes they're going to give you the slope, and they might just give you 1 point. Well, what good is that Well, it does allow you to sketch a line so for example, if we had the point 1, 2 and m equals -3, I should be able to sketch the line based on just this information. And how do we do that? Let's go ahead and put in the point 1, 2. So we have that point there. And then the slope, -3, you really want to think of this on the loving side of this fact that with whole numbers, you can always force them to be in fractional form by writing the whole number over, or the integer, over 1. And then what this tells me is that I have a rise of -3 for a run of 1. Which means that if I start at this point right here and move over to the right 1 unit and just put a little mark there for right now, just kind of hold place. So I moved to the right 1 unit, I ran 1 unit, and then I'm going to rise -3, which means I'm actually going to go down. And I'll go down 1, 2, 3, from 2 down to -1 is a change of -3 units. If I put a point right there after I've run 1 and rise, or not necessarily rise, but drop -3, I will be able to put a line now through those 2 points. And if I were to go to this point, run 1 and drop down 3 more, I should also get another point on the line. So if they give you a point and a slope, all you have to do is plot the point, use the information from the slope to rise and run the proper amounts, and that will get you to the new point on the line, and you connect those 2 dots, and you've got your finished product. One question that does come up is, why do I give the negative to the rise? Just a matter of style for me. I always put the negative with the y value, and I always run to the right. If you want to do it a little differently, you can, and as long as you do it right, you'll get the correct answer. But I found that it's a lot easier to think of just running to the right always, and then if there's a negative in that rise, you just drop down. If it's positive, you would go up. Just makes it a little easier for me, and hopefully for you as well. Okay, so we've got all this information now. We've got the slope in here. We have these points in here. Mathematically, to describe the equation of this line, or to describe this line, I do want an equation. And there are a few different equations that get used in college algebra. The first one we'll look at is slope-intercept. Now, with the slope-intercept form, is y equals mx plus b. Well, what's the m? Well, the m, that's slope. Remember I said m is the letter they use for slope, and well, here it is. So they use the slope there, but the slope multiplied by some x value, and then they add to it this b. And the b is what they call the y-intercept. It's where it crosses the y-axis. Where does this line cross the y-axis? So if we look back here, for example, whatever y value that was right there, that is the y-intercept. That'd be your b value. Down here, that value there, that would be our y-intercept, where the line crosses the y-axis. So looking at this then, it's like, well, how do we get the y-intercept in practice? And I'm going to show you that in another equation here shortly that makes things a little bit easier. But slope-intercept is a very common form, and I want to start out with that. So how does this work in general if you're given slope-intercept and you want to sketch it? For example, if we had y equals 2x plus 1, I would first come over here to my xy coordinate axes, and I would say, all right, the y-intercept, the b, is 1. So on the y-axis, at 1, I know that the line is going to go through there. So I put 1 point there. And then the m, in this case, is 2, or 2 over 1. And we can just use that process that I showed before, where in this case we will run 1, because remember that n equals 2 over 1 will be the same as n equals 2. So we'd have a run of 1, and then we would go up 2 units and get a new point for the line right here. And then I could go ahead and sketch in the line using that information. So slope-intercept form, you have the slope, you have the intercept, and it's very much like what we saw on that last slide where you're given 1 point and a slope essentially. In this case, the 1 point is always going to be on the y-axis, and then you can use that along with the slope in order to get another point, and then you can draw your hopefully straighter line of what I can draw. Right, so that's a slope-intercept form. You should definitely know this, be able to use it, recognize it, and decipher the information from it. The next form we're going to take a look at is point slope. So the point slope form of the line has this basic format where you're going to have y minus y1 equals m times the quantity x minus x1. And this is a very commonly used form of a line when you are given a point and a slope, and you want to figure out what the slope-intercept form is. So this is a very common starting point. And in fact, in other classes, especially if you were to go on in calculus, point slope is a more used form for a lot of the things you'll do in here. So with point slope, let's take a look at an example of this. If you're given a point 3, -1, and your slope given to you as 7/3, and you y minus a -1 equaling 7/3 times this quantity, x minus 3, and you have completed the point slope form of the line. So the thing to pay attention to here, again, is that m is just the slope, and then this x1, y1 is a given point. So once you plug the stuff in, as I have done here, you can solve for y and end up with the slope-intercept form for this particular line. And that's often what they'll ask you to do. You're going to change between a couple of forms. So if we look at this, on the left side, we have y plus 1 equals distributing the 7/3. We'll get 7/3 x, and then minus 7/3 times 3. Y plus 1 equals 7/3 x, and then remember this 3 could be forced to be over a 1, and when you multiply straight across the top, straight across the bottom. But I do see something here where there's a 3 numerator, 3 in the denominator, common factors for that particular multiplication result, and I can just cancel those 3's out and essentially end up with minus 7. Finish solving for y, I will subtract 1 from each side, and we will get y equals 7/3 x minus 8. And that would be the slope-intercept form for this particular problem, where if they asked you to do the point slope, you would stop. Point slope, stop at that place. You might put plus 1, but that's about it. I'm pretty sure they allow you to stop here in the online homework. And if they ask you to simplify down to slope-intercept, you would do this work and get down to that result. Okay, so slope-intercept, point slope, those forms kind of go together. Another common form is what they call a standard form. And with the standard form, this is something that if you were to go into business classes, I see this a lot in the math that is used for business. And it's the reason for it is once you see it here, and let's go ahead and get this down, we'll have a capital A x plus a capital B y equals c. This form allows you to sketch things using what they call the intercepts much easier. So in this case, the way that this book defines it is that the A, B, and C are real numbers. I have seen other classes where they force it to be integers. This book doesn't go that far, but the A, B, and C are real numbers, so nothing imaginary there. And they want the A to be greater than or equal to 0. So they want that leading number out front to be positive. Okay, so let's go ahead and take a look at getting to the standard form from maybe slope-intercept in this case. So example, let's go ahead and convert y equals 7/3 x minus 8 to standard form. And it really is, in this case, a matter of moving things around and, if need be, multiplying the whole equation by a negative in order to ensure that the number in front of the x is positive. So just to kind of illustrate this, I'm going to subtract 7/3 x from each side of the equation. And I will have negative 7/3 x, and then adding in this y that was already there, and this will equal negative 8. The positive 7/3, negative 7/3 x's will add to 0 and go away. This is almost there. However, the problem is that negative. We want the a to be greater than or equal to 0. So what I'm going to do is multiply through the whole equation by negative 1. And when we do this, distributing into each piece, we'll have a positive 7/3 x minus y, and then equals a positive 8. And this would be the standard form for the line that we started with in the slope-intercept. Now again, why is this form useful? Well, it does allow us very quickly and easily to get a couple of points, the intercepts. We've already talked about the y-intercept, where it's going to cross the y-axis, but we also have x-intercepts, where it crosses the x-axis. And for the y-intercept, essentially, when you're on the y-axis, note that right here, the x value is 0. The y-axis passes through x equaling 0. For the y-intercept, we're going to have x being 0, and we'll just go up or down someplace on the y-axis. For the x-intercept, similar idea. Looking at the y-axis, you can see that that x-axis crosses through it when y is 0. And then you'll just have the location of your intercept. So why do I go through this? Well, with our standard form, if you plug in y is, or you want to find the y-intercept, I'm sorry, you plug in x is 0, you just get negative y equals 8, which ends up giving you y equals negative 8. And for the x-intercept, you make y 0, and here we'll have 7/3 x equals 8. Multiply both sides by the reciprocal of what's in front of that x in order to make this properly here. So multiply both sides by that reciprocal in order to get rid of the 7/3 on the left side. And we'll just get x. With that x on the left, because we'll have 21 over 21, or if you think about it where everything just cancels out and you're left with 1 over 1. Anyway, you end up with an x. And then on the right side, we'll have 3 times 8, or 24 over 7. So x will be 24/7, and that'll be our x-intercept. So that's kind of the benefit of that standard form. It allows you to just quickly get 2 points by making x 0 and then y 0 and solve for the variable that's left. And if we were to sketch this, we'd see y-intercept negative 8. So way down here, I'm going to call that negative 8, the point. For the x, 24 over 7, a little bit more than 3. I'll just go ahead and call that right here, x-intercept there. And we would have our line going through those 2 points. So that's the purpose of standard form. Certain books and certain topics, as I said, business, I see that a lot in the business math. They love to use this because it's real easy to talk. Okay, last stuff we're going to talk about in 1.3 is the idea of horizontal lines and vertical lines. For a horizontal line, horizontal, think of the word horizon. When you look out to the horizon is going from left to right. So horizontal line is going to be something that's going to be flat, going from left to right. That's your horizontal line. And for the vertical line, you would just have something going straight up and down. So now when we look at these two, horizontal line, vertical line, how can we write an equation for those? And the nice thing about them is when you look at the horizontal line, the y value isn't changing at all the way across it. Y value doesn't change. If the y value doesn't change, that means that your slope is going to be 0. So really all you need for this horizontal line is to say, all right, well, what is the value, I'm going to label this D where it crosses, what is the value of your y-intercept? You say, okay, well, y equals b. And you're done. Y is equal to 4, let's say. Well, everywhere along that horizontal line, y is equal to 4. Doesn't matter what your x is. X plays no role in the horizontal line equation. For the vertical line, it's a similar concept, except here, the y value is changing considerably, but our x value is not changing at all. And when you go back to that slope form, there's a problem with the slope form when you put in the same x for this point and this point, or whatever points you pick off of there. The x is always the same. When you do that subtraction in the denominator of the slope equation, you are going to end up with a 0 in the denominator. And that's bad math. You have what's called an undefined slope. It's so steep, they don't even know what to do with it. It's not, not a slope by definition that can be found. 0 in the denominator is bad. So this idea of writing it with y equals mx plus b isn't going to work because the m is undefined. So that gets tossed all out the window. And all we have to really do is say, okay, if that x value is a, the equation for the vertical line is just going to be x equals a. Draw that vertical line through there. It'll go through all the y values just naturally, as you can see here. You know, this y values here, 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 and x isn't changing. So all you need to do if you have a vertical line is describe it by x equals the value that your vertical line is passing through. So how does this work in practice? What are they going to ask you to do with these, other than look at them and say, okay, y equals b, x equals a? Well, oftentimes they'll say, find the equation or equations for the horizontal and vertical lines that pass through and come up with a point here, 1, -2. And don't overthink this. All we have to do for this, if we are even going to just look at it, say, okay, well, there's point 1, -2, there it is right there. The horizontal line would be going this way, passing through that -2. So all you have to say here for the horizontal line is y equals -2. Pick that right out of there, you're done. So don't overthink this. You don't even have to draw the picture. You can just say, oh, it's passing this point 1, -2. You want the horizontal line? Oh, what is the y value? That's where the horizontal line is going to go through. That's all you need. Y equals -2. Move on. For the vertical line, let's see here. We would go like so. And it's passing through the x value of 1. So for the vertical line, just say, oh, well, x is always just 1 on that vertical line. Bring it down from the point, and you're done. Again, you don't even have to draw that picture unless it really helps you to see it. You really just need to say, okay, horizontal is y equals something, vertical is x equals something, and you get those somethings from the point that was given. Y equals the y value, x equals the x value. And those are your equations for the horizontal and vertical lines that pass through that point. So it's about where we're going to stop with 1.3. Hopefully this stuff makes sense. If it doesn't, please do ask questions about it in the discussion area. Let's go ahead and move into B4, which is going to be our quadratic equations. Spell quadratic equations. Now, quadratic equation, what is that? Well, in a general sense, you're going to see this a lot. ax squared plus bx plus c equals 0. And that's typically what you're going to see with this. Why do they call it quadratic? I only really see a square there. You know, some people might think we should call this a square equation or something like that. The reason they call it a quadratic equation, remember that quad is a prefix that means 4. Well, they call it that because you have x's, that's 1. You have a, b, and c, 3 more, and 1 plus 3 is 4. So there's 4 items that go into the variables to create a quadratic equation. That's why they call it a quadratic equation and not squared equation, something weird like that. Okay, now what we're going to look at here in this section are a few techniques to solve a quadratic equation. We want to find the x values that would make this equation true. Typically, the a, b, c, they're going to be given to you. You know, you're going to see something like this, where maybe it's 4x squared minus 2x plus 7 equals 0. And your goal is to find the x's that make this equation true. So just keep that in mind. A, B, and C will typically be in there. One thing that we're going to use to our advantage, if we can, in order to solve these equations, is what's called the zero product property. And the zero product property, in very brief speak, this is in your book if you would like to look at this a little more, says that if you have a times b equals 0, then a or b must be 0. That's the only way you're going to multiply things together and get a 0. One of the two, or maybe both. Get this in here, or both. Think about it. If it's 7 times anything that's not 0, you're going to get something that's not 0. You take anything times 10, let's say, and that anything is not 0, you're not going to get 0 as a result. The only way you're going to get 0 out of a product is if one of the two things you're multiplying together is a 0. Well, this is very useful for us if we can factor the quadratic expression on the left side of the equation. Let's put this into play in an example. So if we have x squared plus 5x plus 6, the first thing I'd like to do is see if I can factor this. And in this case, I'm going to have some x's here, plus here and here, and I need some numbers that multiply together to give me 6, but in this situation, add together to give me 5. And factors of 6 are 1 and 6, that's not going to add together to give me 5. 2 and 3, that pair will work. 2 plus 3 is 5. So if I do x plus 2, x plus 3, and I can always do a check with this with factoring. Don't lose sight of that. When you factor it, if you're unsure, or you haven't done this in a while and you're not 100% up to speed on this sort of thing, just FOIL it. Multiply, distribute the x into the other side here, distribute the 2's in, and get x squared plus 3x plus 2x plus 6, and it does check out. We did do that correctly. So all this here is just a check, and it works out somehow. Don't lose sight of that. If you're ever factoring and just want to make sure you get it right, boil it out. Do that distributive process and make sure that you do get back the right thing. Okay, so that being said, I now have this x plus 2 times quantity x plus 3 equals 0. Well, I have two things multiplied together. On the side of that, even though it's a little bigger than what we had up above with a times b, it is technically two things multiplied together. Which means that if we're going to have this equal to 0, either x plus 2 had better be equal to 0, or x plus 3 had better be equal to 0. And if we solve for x, we'll get x equals -2 after I subtract 2 from both sides, or x equals -3 after I subtract 3 from both sides. And this means then that either one of those two x's will satisfy that equation. And if you just do a quick check, do -2 up in there, you'll get 0 times a +1. Well, that's going to give you 0. If you plug in -3 for the x's, you'll get -1 times 0, and that's also going to equal 0. So the answers in this case would be x equals -2, -3. And that's what they will call solve by factoring. So you factor it and then use that 0 product property in order to get to your answers. Is there another way to solve these? Definitely. And depending on what type of quadratic you have, some of these other approaches might be easier than others. So we're going to look at solving by using the square root problem. Now, when you're solving by using the square root property, typically, what you're going to see is something where when you factor it, you end up with something like this. You end up x plus 2 quantity squared equals, I don't know, let's go ahead and say it's equal to 5, something like that. So they've given you this thing where you're able to get this perfect square in there, this x plus 2 square, they call that a perfect square, and then equals something. And with the square root property, we would just take the square root of each side. And it's very important to remember when you take the square root to solve, you better put in this plus or minus on the other side. Why? This. So if you have x squared equals 4, and you're solving for the x in this case, you take the square root of the left side, and you do the square root of the right side, and say, okay, well, the square and the square root will undo each other, and you're left with x. And on the right side, by definition, the square root of 4 is just 2. And you just get x equals 2. Well, that's not the whole story, because last I checked, if you square a -2, -2 times a -2, you're also going to get a +4 out of that. So if you don't put in the plus or minus at this step and carry it through to the answer, you're going to lose one of the answers. So it's very important to put that plus or minus in order to get both answers that will work. Let's come back over to this problem and see that the square and the square root undo each other. We're just left with x plus 2, and in fact, I don't even need parentheses anymore there since I don't want anything outside of that. So x plus 2 equals plus or minus square root of 5. And then we get the x equals negative 2 plus or minus square root of 5. We're subtracting 2 from both sides. In the online homework, they are probably going to want you to write it like this. Negative 2 plus the square root of 5, comma, negative 2 minus square root of 5. I don't know if they have a plus minus option in the online homework, but for an exam, I'd accept that. Or in homework, you might have to write that. So that's using that square root property. Now it is kind of a cooked up case here. You know, these square root properties seem to only work when you have a perfect square. And it's like, well, is there any way that I can, start with something such as what I started with up here, this x squared plus 5x plus 6, and use the square root property? And in fact, there is an approach called completing the square, which allows you to make that perfect square and then use the square root property. And these are all techniques where, if you recognize that it can be factored, I highly recommend you use that one right away. That's going to be your quickest bet. But if you can't factor it, you might want to use this solve by completing the square approach. And there is going to be another approach I'm going to show you here in a moment that is good for anything. And, I usually just go straight to that one if I don't see factoring right away. But it is important to know how to complete the square in this class. So that's why I'm showing it. That's why they're going to ask you to do it. There are places, especially when we get into the conic sections part of this book, where you are going to have to complete the square. And if you don't know how to do it, you're going to be struggling. So let's take a look at solving by completing the square. So solving by completing the square, let's go ahead and just take a look at an example. Squared plus 5x plus 6 equals 0. So we've already seen the answer to this. But I want to just show you how to get there in a different way. And with completing the square, again, your goal is to have x plus, I'm just going to put a letter there to hold place, x plus something, maybe a minus something, squared in the mix. So we got to get this perfect square. We already saw how we factored this up above, x plus 2 times x plus 3. It's not the same thing that I can just write as maybe x plus 2 squared or x plus 3 squared. Yeah, that's not going to work. So how do we complete the square and make a perfect square? Well, first step is to ensure that the number out in front of the x squared is a 1. And I will show an example of when this is not a 1 to help you out a little bit here after this one. So x squared, got to have a 1 in front of that. And we'll have plus 5x. And then what I'm going to do here is I'm just going to put in a little blank to hold in place for something. And I'm going to move the 6 to the other side, do subtraction. And I'm going to put in a blank over here. Now, why am I putting these blanks on both sides? Well, on the left side, I'm going to put there to house the number that will allow me to write this as a perfect square on the left side. And if I add something into the left, I want this equation to maintain balance. I don't want to have this be different. So I'm going to have something added in on the left. Well, I better add in that same thing on the right in order to maintain the balance of the equation. What you do to one side, you must do to the other. So in order to get the number that I need to add in order to complete the square, you take, change colors here. You take the number in front of the x to the first power and have it. So divide it by 2. and then you square it. So you get 5/2 squared, and that in this case is going to give us 25/4. And then on the right side, we also have 25/4 added in. Now this number, 25/4, is the number I need to add in to complete the square, which will allow me to write this equation now as x plus just 5/2 quantity squared equals this -6 plus 25/4, and I'll deal with that here in a moment. And I've completed the square. But if you're looking at that x plus 5/2 over, or I'm sorry, x plus 5/2 quantity squared, and asking yourself, how is that going to get me back to x squared plus 5x plus 25/4? Remember, it's just going to be an aside again. Remember that x plus 5/2 squared is equal to x plus 5/2 times x plus 5/2. And we'll FOIL this out, so we'll be out, and we'll get x squared plus a 5/2 x plus another 5/2 x plus 25/4. Well, 5/2 plus 5/2 is 10/2. And 10/2 reduces to 5. X squared plus 5x. That is not long enough quite good. I'm just making a mess. So it does always work out where whatever you get when you take half of that number in front of the x, that is the number that goes into the parentheses to complete the square. You do need to square that number so you know what you have to add in to the right side to keep it in balance. But just keep that in mind as you're going through this process. Okay, so I'm going to go ahead and simplify the right side of this. And -6 can be adjusted to have a common denominator by writing it as -24/4, so that I can add it to 25/4. And this becomes just a positive 1/4 on the right side. And now here I have something that allows me to use that solving by the square root property. I can just take the square root of each side now and solve for the x. And remembering to put in a plus or minus. So our square root undo each other. We get x plus 5/2 equals plus or minus the square root of 1/4. Don't lose sight of this. The same thing as the square root. Square root there. Square root of 1 over the square root of 4. Properties of roots allow you to do the numerator and denominator separately. Square root of 1 is 1. Square root of 4 is 2. So we're just going to have plus or minus 1/2 on that right side. And we will get x equals -5/2. We'll subtract 5/2 from both sides. Plus or minus the 1/2. And if we take a look at where this gets us, -5/2 minus 1/2, which will be -6/2, which equals -3. That should look familiar from above. And then we'll also have -5/2 plus 1/2 equaling -4/2, which equals -2. So if we go way back up to the original problem and see what we got when we were able to use a factoring approach, -2, -3, we get the same exact answer using completing the square. And you're probably at this point, hopefully, realizing that if you can solve by factoring, that's going to be your quickest and most efficient method to get to an answer. But solving by completing the square is also something that you need to know how to do. Let's take a look at one more example of solving by completing the square that's maybe not as trivial, but illustrates that when you have a number in front of the x squared, you've got to get it out of there. So I'm going to go ahead and do this. Let's see here. Let's see what this does. Okay, so when you're solving for x in a situation like this by completing the square, you are going to first have to get that 2 out from the x terms. Factor it out. Not even worried about the number out back. It's just going to get moved around anyway. So just factor that 2 out of the x squared and x terms. I'm going to move that 7 to the other side. And I'm also going to put in a little blank here that allows me to add something in so I can complete the square inside those parentheses. Get that back to green. Now on the right side, I still want to keep this equation in balance. This is very important. We're going to add something in on the left, better do it on the right. What we have to be careful with on these types of problems, when you have a number in front of the x squared to begin with, and you factor it out so you can do the completing the square process, which does not work. And you can try it all day long. It's not going to work if you have a number in front of that x squared that you don't deal with. Looking at this problem, it's like, well, inside that parentheses, whatever I add in is really getting multiplied by the 2 out front. You know, when you distribute stuff back in, you distribute 2 and distribute 2, distribute 2 in. Well, it's going to change that number that you add in to complete the square by a factor of 2. So for these types of problems, if you got a number out in front of a parentheses when you continue the square, before you go and add in this blank on the right side, go ahead and put a 2 there. It's going to be double anyway on the left. You better double it on the right in this case. Yeah. So very important to make sure that whatever you pulled out of there, you incorporate it into the right side as well. Right, now in this case, we have 2 here. I'm going to take half of 2 and get 1. I'm going to square 1. And 1 squared just becomes 1. So on each side, I'm just going to put a 1 in, fill those blanks. Okay, now on the left side, I have 2. I'm going to have x plus 1, 1 squared. On the right side, I'm going to have 7 plus 2. And we will end up with 2 times x plus 1 squared equals 9. Before you can use the square root property, it's a good idea, and technically you can get away with not doing this as long as you keep math straight. But I find it's a good idea to get anything in front of the parentheses, divide it out. So I'm going to divide those sides by 2 in order to get that x plus 1 squared alone. And we'll have this equaling 9 halves. And now I can go ahead and get the square root of each side. And remembering the plus or minus. And I will get x plus 1 after my square and square root cancel equals plus or minus. Remember, we can do numerator and denominator separately. So the square root of 9 is 3 in the numerator. Square root of 2 doesn't have an answer, so we got to write it like that. I'm okay if you do not rationalize the denominator. Something that some books are pickier than others, and you do want to pay particular attention to the answer boxes and the instructions beneath them. They say rationalize the denominators, things like that. Make sure you're doing that. But on a test, if you were to leave it like this, I would be okay. Now I'm going to subtract 1 from each side, get x alone. And this to me is a perfectly acceptable answer. I would love to see that on an exam for this problem. Or if you are one of those people that just cannot do math without rationalizing, you would end up with the 3 root 2 over 2 for that fraction. So either one of those two I would solve. That is solving by completing the square. Okay, last thing we're going to look at, and this is something that, you know, especially once you get out of college algebra, as I said, if I can factor it, I do. If I recognize it can be factored, I go ahead and do that. If I recognize that I can't factor it, or maybe it can't be factored, I will go ahead and jump straight to this next approach, which is solving by using the quadratic formula. And the quadratic formula will work for any quadratic equation that you're given. It will always work, always give you an answer. And I've known some people that all they remember is the quadratic formula, and they don't care about anything else. Where does this come from? Where does the quadratic formula come from? And you may have seen it before, the negative b plus or minus the square root of quantity b squared minus 4ac all over 2a. But I do want you to learn some more things in college algebra than you may have learned in a high school class. So how is it derived? Let's go ahead and take a look back at the original basic form for your quadratic equation. X squared plus bx plus c equals 0. And from here, what we are going to do, because there's a unknown, you know, I don't know what a, b, and c are. I don't know if I can factor it or not. I'm going to go ahead and solve this by completing the square. So let's go ahead and factor that a out, because if that a is not 1, I've got to get it out there in front. So I have a out front, and then x squared plus b over a x. Remember, when you're factoring stuff out, you want to be able to multiply back in and get what you started with. So if we do a times x squared, I get bx squared. A times b over a, the a's will cancel and leave me with bx. So that's going to be nice. And then I'm going to go ahead and put in a little blank here because I'm going to add some stuff in and put the square in these parentheses. The c, I'm going to move that to the other side. So I have negative c over here, and then I have plus a times something, whatever I have to add in to complete that square. I'll go ahead and continue trying to having my blanks the same color. All right. So this is where, you know, things get a little crazy with the letters and symbols, but you know, you got to rewind this a couple times to get through it. It'll be all right. It's something I feel it's good to see where this formula comes from. Right? It didn't just fall out of the sky and work for some reason. Coming down here, I'm going to take half that b over a, which means we're going to have b over 2a. And then I'm going to square it. And we will get b squared over 4a squared. Add it in. If I square the numerator, square the denominator quantity, that's what I get. It means over here, I better have b squared over 4a squared as well. Add it in. So continuing with this, I can now write on the left side, a will have x plus b over 2a quantity squared. And this will equal then negative c plus, if I distribute the a in, keep in mind again, this a is going to be over 1, forced it to be a fraction. When we multiply that in, we're going to get b squared over just 4a. One of the a's will cancel from the numerator and denominator. And now at this point, I'm going to divide out by another a. So we'll have x plus b over 2a all squared equals, if I divide the whole thing by a here, I'll have 1 over a. And when you divide by something, it's equivalent to multiplying by 1 over that something. And so getting closer here. I'm not going to take the square root yet. I just want to clean this up a little. So we have negative c over a, distributing the 1 over a into that term, and then plus b squared over 4a squared. So that's coming in again. Squared in there. I want to get this right side cleaned up a little more. It's going to make this pop out a lot better if I do this. I need a common denominator, which means that 4a squared needs to be the denominator for both terms. I need to multiply the first expression by 4a in the numerator and denominator to get 4a squared down below. So 4a times top, 4a times bottom. And then plus this b over 4a squared, or b squared, sorry, 4a squared. And some of you who know the formula might be starting to recognize things at this point a little bit. So what I'm going to do now is just reorder this, get it all over that common denominator. We have a positive b squared minus the 4ac. Rewriting that numerator with the b squared out front, and then still having a negative 4ac following. This over 4a squared. And now I can take the square root of each side. And I have that plus minus in there. And on the left side, we get our square and square root, undoing each other, thankfully. We get x plus b over 2a equals, I can still do the numerator denominator separately, so my plus or minus the square root. I don't know what square root of b squared minus 4ac would be, so I'm just going to leave that as what it is. But down below, the square root of 4a squared, square root of 4 is 2, square root of a is a, so I can just have 2a in the denominator. And last but not least, I need to subtract away negative b over 2a from each side to get the x alone. And what we end up with, we already have common denominators, will be negative b plus or minus square root of b squared minus 4ac, all of them 2a. And that is your quadratic formula. And that is what I would expect you to know if I were to ask you to solve by using the quadratic formula. Got to know that formula. You will be allowed to use a note card on the exam, so that could be helpful, but you're going to be using this. Big question that may arise is, am I going to ask you to reproduce the derivation of this formula? No, I am not. But this is college. It is algebra. Putting those two things together, get our college algebra. I want you to see a little bit more than what you have seen possibly in high school. I want you to realize where this formula comes from and know that, again, it just didn't drop out of the sky and started using it. So it all falls out of that completing the square process. It's another reason to appreciate the completing the square. Let's take a look at an example of this, and then we'll call it a day. So solve. Let's see, let's do a negative x squared plus 5x minus 3 equals 0. So where that gets us. negative x squared plus 5x minus 3 equals 0. In order to use the formula, we need to know what our a, b, and c values are. In front of the x squared, I see a negative. Well, remember that there'd be like a little 1 there when they don't write it. And there's nothing in front of the x. You can always assume it's a 1. So we really have a equal negative 1. B, remember in front of the x to the first power is 5, and c is negative 3. All I have to do now is put those values into the quadratic formula and see what we get out. So here we're going to have x equals negative b, or negative 5, plus or minus square root of 5 squared minus 4 times negative 1 times negative 3 times that a, c, all over. Very important, put everything over this. I see some people that only draw the fraction bar under the radical, then you get the wrong answer, then you cry. Don't make yourself cry. Put the fraction bar underneath, or I should say, underneath everything. So make sure you keep that. So x will equal negative 5 plus or minus the square root of 5 squared is 25. We have negative 4 times negative 1, which is a positive 4, times a negative 3 is going to be a negative 12. So 25 minus 12 all over negative 2. Not much back here now. And what we will end up with now here is negative 5 plus or minus the square root of 13 all over negative 2. And what they may go ahead and do is move these negatives around a little bit from the denominator up to the numerator, and you end up with x equals a positive 5 minus plus square root of 13. We'll talk about this in a moment, over the 2. And maybe asking, whoa, wait, what did I just do? Again, with this negative here, you can think about it as negative 1, and the negative in the fraction, I can move that around, and it doesn't matter if it's in the denominator or the numerator. So really, this is equal to a negative of the negative 5 plus or minus the square root of 13 all over the positive 2. It's an equivalent expression. Distributing that negative in, we'll get a positive 5. Then the plus or minus becomes a minus plus. The negative plus plus be minus. The negative with the negative gives us the plus. But it's still a negative and a positive case. Positive, negative, negative, positive. It's still the same thing. So we could just go ahead and call this 5 plus or minus 13 over 2. And that would be an acceptable answer. In homework, they would probably ask you to write this: 5 plus root 13 all over 2, comma 5 minus root 13 all over 2. So this problem again, if you try to use factoring approach, well, good luck with that. If you tried to complete the square, you would get down to that same answer, but by having this formula, we avoid having to go through all these steps like we did when we derived the formula. We just have to plug stuff in, and we get to that final result. Okay, that's going to end the material for week 1. If you have any questions on this material or this lecture, please ask them. The only way you're going to learn the material is to ask questions when you don't understand. So make sure you do ask them. Otherwise, hope you have a great week, and I will see you in cyberspace.